so we have been talking about B spline curves, right? So we'll continue on it. Let's have a bit of a recapitulation of some aspects which we saw last time. So what we observed in the case of B splines, that B splines enables for us to define for each control point an associated unique basis function. Right. So, in turn what happens is that the influence, the way a point on the control polygon affects the shape of the curve, it actually is in a range of the parameter values. Right. It is not the entire range of the parameter values, but it is a sub range of the parameter value, and in turn we get the local control, which is not the case in the case of Bezier curves, right. So, and also we observed that these B splines help us decoupling the order of the curve or the degree of the curve and the number of control points you specify for the B spline polygon, right. Okay. We also so the functions, the polynomial spline function which is used as a basis for B splines basically defined as these nik's, where k is the order of the curve. So, therefore, it ranges from 2 to n plus 1, where n plus 1 is the number of control points you specify, right. So, the maximum order of the curve which you can obtain is n plus 1, and the parameter t ranges from some t minimum to t maximum, right, and these BI's are nothing but the control points. So, this is a very standard way of defining the parametric curves as some sort of a blending of the geometric information specified through the control points, right. And if we see how these nik's are computed, so they are computed in a recursive manner, where the base case is for ni ones, which is nothing but a some sort of a step function defined as 1 or 0. So, it is 1 when the parameter t is in the not values x I to x I plus 1. So, there is also a notion of not vector, which are in some way are the junction points for the parameter domain for the curves which is defined, right. So, x I and x I plus 1 are nothing but the pair of knots, right. And then the nik is just defined as a recursive in a recursive way using the nik minus 1s and ni plus 1 and k minus 1, right. So, these are some combination of these, and the x I, as I mentioned, they are the not values, and there is a property to these not values that they are monotonically increasing, right. And we in particular observed that there could be number of ways in which we can define or give the x values or the not vector x. So, they could be uniform x or uniform not vector or periodic not vector. Periodic because the nik's which are computed using these knots turn out to be periodic in nature, right. Or it could be open uniform. So, there we have the multiplicity of the knots at the two ends, right. So, the knot is repeated k times at both the ends of the knot vector, right. And they could be non uniform knot values where the interspace of the two knots may not be the same, right, or even the internal knots in the case of open uniform may be repeated, right. So, these are the various kinds of knot vectors which we can specify. Okay, so, the properties which we observe, number one which is missing here is actually the partition of unity, right. So, the summation of the nik's equals to 1, right, and all these nik's are non-negative, right. So, which in turn gives us the nice property of the curve residing within the convex hull, right. So, that is what here is mentioned, and in fact, we observed that this convex hull property in the case of B splines is tighter or stronger compared to the Bezier curves, right. And we also observe that the curve which is designed actually follows the shape of the defining polygon, right. So, that is the notion with which the Bezier curve started, where you could specify the points and the curve which is obtained follows some sort of the shape of the polygon. In a similar way, B splines offer you that property, right. And in fact, the fact we also observed when we considered the knot vector to be an open uniform knot vector, right, and when the order k is equal to the number of control points n plus 1, the B spline is nothing but the Bezier curve. So, therefore, Bezier curve is a special case of B splines. So, all those properties which we had observed in Bezier curves are sort of carry forwarded to B splines, right. So, here we observe that the maximum order of the curve, which actually in the case of open uniform knot vector, when equals to number of control points, it is a Bezier curve, and therefore, the maximum order which we actually can construct using B spline is the number of control points, right. So, the other properties which we had seen earlier, so some of them I have listed here. For instance, just the way Bezier curves are invariant to affine transformation, right. So, if you recall, invariance to affine transformation means that if I apply an affine transformation to the Bezier polygon, right, then the curve computed after the transformation, right, is the same as if I had applied the affine transformation to the curve itself, right. So, that property holds even in the case of B splines. Similarly, they also exhibit the property of variation diminishing, right. So, the turn and the twist which you have for the spans of the polygon, right, the curve has less turns and twists, right. So, if you take a line and in a planar curve, if you take a line and find out the intersections it would have with the polygon, the number of intersections it is going to have with the spans of the polygon is going to be more than it will intersect with the curve itself, right. That is what variation diminishing is, right. So, they also exhibit this property. Okay. So, let us try to see some of the control handles by which you can manipulate the shape of the curve, right. So, clearly, if we see the parameters which are involved in the process of constructing these B splines, some of those parameters are towards the control handles of those curves for the shape of the curve, right. So, for instance, you could have possibly the knot vector to be uniform or should be actually open uniform. So, uniform is the same as periodic, this is open uniform, and then you have non-uniform. Right. So, this is periodic, open uniform and non-uniform, and each one of them would actually give you a different shape of the curve because of the fact that they determine the basis function, right. Clearly, the order of the curve k also has a role to play for the shape of the curve, right. We will see some of the illustrations of this aspect. Number and position of control point definitely plays a role for the shape of the curve, right. So, let us see the control handle in terms of the order. So, let us say I consider the knot vector to be open or open uniform knot vector, and I have the control polygon as B 1, B 2, B 3, B 4, right. If I have k is equal to 4, right, which is the same as the number of control points I have a Bezier curve, which is given here with this yellow line, right. If I change the order to k is equal to 3, that means I have a second degree B spline curve. The curve looks like this, right. And in fact, in some ways it is sort of a combination of, let us say, two curves, possibly a point here, right, quadratic curves passing from here and the other quadratic curve passing from there, right. And if I have k is equal to 2, that means degree equals to 1, then the B spline is nothing but the polygon itself, right. So, this is the B spline you have. Right. So, what we observe is that as we change the order, there is some sort of a slackening of the curve, right. When I have the order to be, let us say, the maximum order I could possibly have, which is number of control points, the curve was quite tight, right. That is the shape of the curve, and as I change the order or reduce the order, the curve sort of slackens, right. And in a limiting case, it goes to the polygon itself, right. And some of it you can also map to its convex hull property, right. So, what does convex hull property say? That the curve resides in the k neighboring control points, right, union of such convex hulls. So, that is what you can also see, that since the k is changing, right, the curve is sort of going towards the control polygon, right. Similarly, let us try to see the aspect of number of control points, and when I say number of control points, it is not just the number of control points to define the B spline polygon, but also see the multiplicity of those control points. Okay. So, again, if I consider the knot vector to be open uniform knot vector, and let us say I fix the order as k is equal to 4. So, initially I have the curve here, which is again the Bezier curve specified through these control points B 1, B 2, B 3, B 4. Right. Now, what I do is I duplicate the point B 2, right. So, this B 2, I add another point at the same location as B 2, that is what I mean. this multiple point, right. So, the control point polygon is actually now B 1, B 2, B 2, B 3, B 4. Okay. So, one has to be careful putting the right index, though. I am just repeating B 2 for the purpose of telling you that this point is repeated, right. So, what we observe is that the curve actually goes more towards the physical location of B 2, right, and which makes sense, because I have added another point there. Therefore, it has to act like an attractor to the curve, right, and the curve would actually go towards that point, right. Now, what happens if I further repeat it? So, the curve actually passes through the control point B 2 itself. Okay. Right. Now, because again if you sort of try to map with the convex hull property, what is happening is that you have the curve with k neighboring points, so B 1 3 times B 2, the curve is nothing but the line itself, right. So, we see the effect of using multiple control points, multiple vertices for the control points, right. Okay. The next let us say the control handle is the position of the control point itself, and that is the basic purpose of having these parametric curves using control points, right. As you change the position of the control point, the curve has to follow the shape of the control polygon, right. That is the inherent property we want to capture. So, let us say I have again a B spline defined through the control points, let us say from B 1 to B 8, again using open uniform knot vector, and of the order k is equal to 4. Okay. So, now if I take the control point B 5 and change this position to B 5 prime, right, what I observe is that only a portion of the curve actually changes its shape. Right. So, there is a portion of the curve here which does not change, there is a portion of curve here which does not change, right. And when I further move this B 5 prime to B 5 double prime, you see this curve change to this, right, and that exhibits the local control of the B splines. So, there is only a certain range of the curve which is influenced by the movement of the control point, right. Of course, that range would depend on the order you are using of the curve, right, and how many control points you have and so on. So, in this case, in fact, it turns out you have k by 2 times on the left side of the control point which is moved, right. So, when I moved B 5, basically the curve for the spans of B 3 B 4 and B 4 B 5 and spans for B 5 B 6 and B 6 B 7 alters. Okay. The spans covered by, let us say, plus minus k by 2 from the point which is moved, right. So, that shows the local control, and that is what we wanted to have to start with. Is it clear?
So, what are the could you just repeat what is the convex hull property state in terms for example here k is 4,
right,
then it states that the number of some points,
the neighboring k points, right,
neighboring k points. For example, if we have b5 prime here,
right,
b5 prime,
right.
then the curve would lie between b3 to b7.
No, so I will take the union of the convex cells defined from b1, b2, b3, b4,
Okay.
b2, b3, b4, b5,
Yes.
b3, b4, b5, b6, right? It's a convex cell, remember that. This is a convex cell, so it always will reside in that.
Yeah.
And b5, b6, b7, b8, right? So there might be some little error because these are hand drawn curves, so they are not actually computed curves, right? So that property has to hold. Okay. So the next thing is, as we are talking about these control handles, right? So let us say we want to augment these controls towards the change of the shape of the curve, right. So what we have is another variation to the normal B splines, which are rational B splines, where let us say if I define the curve in a homogeneous coordinate system, right. So if I am trying to define a 3D curve, I am basically defining the curve using 4-dimensional coordinates, last coordinate being the homogeneous part of the coordinate. That is, let us say if I put this h here, that is for the homogeneous coordinate. Then the rational B splines are nothing but some sort of a projection of these non-rational or the regular B splines which we have seen defined in 4D space. So, if I am trying to get the rational B spline defined in 3D space, if I consider the non-rational B splines defined in 4D space using homogeneous coordinates, then the projection of that is what I get as rational B splines, right. So, if you remember when we want to, let us say, display or render the primitives, we divide by the homogeneous coordinate in order to get the primitive in Cartesian or the normal coordinate system, right, the physical space. So, what happens to this is that when I would divide by the homogeneous part of the coordinates, I will basically be dividing by this, right. So, these h i's are some additional coefficients which I am using here, right. So, these are sort of the homogeneous part related to the B spline control points. They are also referred to as weights, because they are acting some sort of a weight to the definition of the control points. So, what do I have is some sort of a rational basis functions, right. So, now I can look at these basis functions which are defined through the use of the niks and the hi's, right. So, these riks are nothing but these combinations using hi's and niks, right. Is it okay? Now, in fact, this formulation still captures most of the properties we have observed in B splines and offers some additional. Okay. Now, so if we look at now the formulation of these rational B splines, so what we observe is that this is sort of a generalization of the non-rational B spline basis functions and the curve, because we can arrive at the non-rational form of the B splines if I substitute all h i's to be unity, right. So, the non-rational basis functions or the curves are nothing but special cases of rational basis curve. So, most of the properties and characteristics of the regular B splines which we have seen, or the non-rational B splines we have seen, are carry forwarded. And what we get is an additional parameter which is h I for further controlling the shape of the curve, right. And one of the motivations to have this rational B splines curve is to enable the construction of some of the common analytical shapes, such as conic sections. So, for instance, perfect circle, ellipse, parabola, right. So, even though you can have closed curves in the case of B splines or Bezier curves, but you cannot construct perfect circles, right, which you can if you use rational B splines. Okay. So, there is an additional property which is offered through rational B splines. So, if you remember, we have looked at the affine invariance property of the B splines, right, and we posed this question when we were talking about Bezier curves: does this have projective invariance property or not, right? And we said no, it does not have. Now, if you look at now the construction of rational B splines, right, the way these are constructed, when we are assuming these h i's to be some sort of a homogeneous coordinate for the Bezier, for the control points of the B splines, right, then the process itself shows, because what we are doing, we are taking the projection of those curves defined in a higher space, right, 4D space in the case of 3D space curves, or 3D space in the case of 2D space 2D plane curves. Then we have the property of invariance to projective transformation, right, which means that if I apply a projective transformation to the control points of the B spline, it is equivalent, and when I reconstruct the B spline curve, it is equivalent if I apply the same projective transformation to the curve, right. And I am not giving you the proof of it, but it is not very hard, you can prove it. As I said, that just the way the construction goes using those rational basis functions, you can actually prove that, right. So, this is an additional property or the characteristic which is offered through rational B splines. Okay. Now, just to give you an example, particularly to demonstrate the use of this h as some sort of a weighting coefficients or parameters, right. So, what do I have is the number of control points I have is 5. So, n plus 1 is equal to 5. The order of the curve which I am trying to construct is 3, right. So, I have these control points B 1, B 2, B 3, B 4, B 5, and the order is 3. And if I use the open uniform knot values with k repetitions at both ends, and starting, let us say, the knot vector at 0 with integer increments, this is what I will get as the knot vector, right, where the size of the knot vector should be n plus 1 plus k, right, and the corresponding, let us say, h vector, which is nothing but the h or the weighting factor with respect to each of the control points, which also can be interpreted as the homogeneous part of the coordinate for these control points, right. So, let us say if I assume that h is 1 for B 1, right. So, small h 1 is 1, small h 2 is 1 again, and small h 3 is some value there, and for B 4 and B 5 these are again 1, right. So, I am just looking at the change of this weight factor or the value of h for one particular control point, right, which is for B 3. So, what happens when I change h 3? Okay. So, if I have h 3 is equal to 1, which is the case here, I have the normal or non-rational B spline, right. Now, when I change h, let us say to a value which is greater than 1, let us say some value like 5, again it is to say that the weight of this particular point is 5 times compared to the rest of the points. Therefore, the curve goes towards P 3, right. So, that is a control handle for the shape of the curve. Similarly, when you decrease the value of h, lower the value of h from, let us say, 1 to some other value 0.5 for instance, right, it sort of goes away from B 3, right, because the weight factor now of this particular point is just the half compared to the rest of the points, right. And you can also have h equals to 0, and when you see that there is no contribution from this point almost, and the curve is there. Right. So, what we observe here is this change of the value of h is also in a way controlling the shape of the curve, just the way we were trying to move or displace the points, right. So, we do not perhaps need to displace the points, or additionally we can use this h as for controlling the shapes, right. We have seen the formulation of rational B splines here. Now, the question is, if I am talking in terms of having rational Bezier curves, I should be able to have it, right, in a very similar way. So, I can also introduce the concept of having the weight or these h coefficients for defining Bezier curves, right. The only change is that the polynomials which I am going to use will be Bernstein polynomials there, right. Okay. So, that sort of takes care of the variations in terms of what we can get for controlling the shape of the curve for B splines, right. Just to make it clear, the examples which we have observed are, most of them are planar curves, right, but extending to space curve is just a direct extension, right, because these are parametric values. So, if I am talking about x t, y t, the same thing applies to z t, right. So, that way you should not think that we are only dealing with planar curves, right. because it all depends what is the dimension of your control point, right. Okay, so now I am going to pose a before actually I do that. So, you must have heard the term NURBS, right, it is very popular. So, have you ever NURBS, NURBS? Okay. So, these are nothing but some sort of B splines. In fact, these are non-uniform rational B splines. Right. So, therefore, these NURBS are the most generalized form of B splines, because we are talking of rational B splines, right, which is a superset of non-rational B splines, and non-uniform is the most general form of the knot vectors we can specify, right. So, this enables you to have non-uniform knot vectors and the rational basis functions for B splines. So, the rest of the B splines could just be the special case of NURBS, right. So, for instance, there are certain primitives using NURBS in OpenGL. So, you can define the appropriate values for the control points for the order of the curve and give the knot vectors to construct these NURBS, right. Okay, so, now I am going to pose a problem which I said so far. What we have seen is that these B spline curves or the Bezier curves, as opposed to cubic interpolating splines, are the curves which do not pass from all the control points. Control points only govern or control the shape of the curve, right. They may pass from the endpoints, right. So, for instance, in the case of B splines, if you have the open uniform knot vectors, there is a multiplicity of knots at the two ends, the curve passes through the endpoints, right. So, now the question is, let us say if I want to obtain B splines passing through data points, right. So, what are we addressing? We are trying to address the problem of curve fitting. I have these points D1, D2, D3 and so on to Dj. These are the data set, the data values or the points, and I want to fit a B spline through these data points. So, how can I do that? First, the question is, can I do that? Hopefully, the answer is yes, right. How can I do that? You understood the problem, right. So, we are given these data points D1 to Dj, and we want to construct a B spline passing through these data points. So, see, for the construction of the B splines, what do I require? Let us try to investigate that first. I require control points, right. So, if I am able to devise a mechanism to be able to find control points, which would in turn make the curve pass through these data points, I have solved the problem, right. So, we are posing the question that can I find out those control points, given that the curve passes through these data points. So, if you look at the way we define these B splines are through using the control points B i's and the n I k's, right, where k could possibly vary from 2 to n plus 1 for some parameter value t. Fine. Now, when I say that this curve should pass through the data points, so I am basically imposing the constraints to this curve. So, the point d1 for instance, if the curve has to pass from this point d1, then I can say that d1, which is nothing but the evaluation of the curve at some parameter value t1, should be possible to be obtained from there, from the definition of the curve, right. If I use some b1 to bn plus 1 control points, right. So, similarly, I can set these constraints, right, in the form of the equation which the curve needs to satisfy, right. So, I am setting a system of equations to be solved for B i's. That is what I am doing, right. Given some k, I can compute the appropriate values of n I k's. I still require the definition of t, right, and that should be possible maybe through the data which is given to me, right. Okay. So, if I set this as a system of equations, so this is what I am doing. These d's are the data points, the b's are the control points, and this is nothing but the coefficients from the basis functions n I k's, which could also be represented as in the form of a matrix, right. So, clearly, if I set this as a system of equations, I can solve for b inverting n and multiplying to t, right. And if I have the number of data points, which is j, is the same as n plus 1, which is the number of control points which I am trying to compute, then I get this n as a square matrix, which I can invert easily and obtain the corresponding control points, right. And if this is not the case, or if this is what you do not want to impose as a condition, where the number of control points is the same as number of data points, typically you would like to have less number of control points, right. Then the system of equation is what you obtain is overdetermined, right, and then you will have to apply some kind of a pseudo inverse to the solution of the problem. D is equal to n b in the matrix form, where D is the vector of the data points and n is the matrix formed of the basis functions n I k's, and b is the set of control points. Now, in order to be able to solve for this b, what I can do is multiply with the transpose of n both sides, right, which gives me n transpose d equals to n transpose multiplied by n and b, right. Now, I can actually take the inverse of this, right. So, we are basically considering this situation where I may not require or may not want to have the number of control points to be the same as the number of data points, right. But this would enable me to have the inverse of the matrix n t multiplied by n, and then I can solve for B, which are the control points, as this, right, n transpose multiplied by n inverse multiplied by n transpose D, right. So, the resulting B spline which I would obtain using this pseudo inverse solution would not pass through exactly the data points. This will be very close to the data points and may pass through some of the data points, but may not pass through all the data points. But that is something which one may want to compromise by reducing the number of control points you want to obtain corresponding to the data you have for fitting, right. So, this enables us to have a B spline curve interpolating the data points defined through D. Now, one of the things which is still to be determined are the parameter values t, right. So, the question comes, how do we compute these parameter values t? So, if you recall, we have discussed the parameterization in cubic interpolating splines. So, we had uniform parameterization and we also had chord length parameterization. So, in fact, what we can use is something like chord length parameterization even here, which is something like this. Let us say I am trying to evaluate the parameter value T j for the data point D j. Then for nth data point, if I consider the ratio of T L to T max. So, T max is nothing but the maximum value of the parameter, which I could actually consider as the maximum value of the knot vector, and given that let us say the initial value of the parameter, which is T 1 equals to 0, then I can obtain the intermediate values of the parameter like T L as a distance measured as a chord length for the data 2 L, right. So, S is equal to 2 to L divided by the data covered till I have obtained the data point. So, let me illustrate this, that might be a better way to understand. So, what I am trying to say here is, let us say I am evaluating the parameter value at D 2, right. So, what I am looking at is the ratio of T 2 to T max, which is nothing but the distance computed of D 2 from D 1, which is this chord length, to the ratio computed for the entire data set chords. So, in this case, the total sum of the length of the chords, which is this chord and this chord. So, we are considering a problem where we have 4 data points D 1, D 2, D 3, D 4, right. So, the ratio of the parameter value computed T 2 for the data D 2 is the chord length D 2 minus D 1 to the entire sum of the chords up to the last data point, right. So, chord length D 2 D 1, D 3 D 2 and D 4 D 3, right. So, in some sense, what are we trying to do? We are trying to obtain the information of how the data is arranged in terms of its span from different points, right. So, in this manner now we can compute the parameter T L for any data point, right, and assuming that T max as the maximum value of the knot vector. This way we can span the entire knot vector as a useful parameterization for the curve which we are going to generate, right. So, we are trying to capture the location of the data through this parameter value T, considering the chord lengths, right. So, chord lengths are always better parameterization than the uniform parameterization, because they have in some sense the location of the point embedded in the parameterization. So, this way we can obtain the interpolating B splines passing through a given data points, right. So, that takes care of, let us say, the various curve generation using interpolating splines, using Bezier curves, B splines, and even obtaining the B spline curves or even Bezier curves interpolating to the data points, because once we can have B splines, we can also have Bezier curves, which are special case of B splines, right. So, I would like to end here about curves. We will start next time discussion on surfaces. Thank you.